This is a lesson that is part of an introduction to energy storage elements, specifically inductors and capacitors. And in this lesson, I want to introduce you to the usefulness of inductors and capacitors as energy storage elements in a class of circuits, a very important class of circuits used in power conversion. And these are called switching power supplies or switching power converters. And they are everywhere. You will find them in your little iPhone charger, your computer power supplies. It's what makes our plug-in power supplies lightweight and not a big chunk of iron as they were years ago. And central to those circuits being able to accomplish what they're accomplishing in regards to power conversion is their useful utility of inductors and capacitors along with high-quality switching transistors and diodes. And so at this point in the course, I want to introduce you to this because you have everything in hand to at least appreciate an initial glimpse at the principles behind switching power conversion. And furthermore, we're planning a lab for you where you will build one of these converters and observe its operation. So this is preparation for that lab. So at this point, what you should be familiar with in terms of capacitors and inductors are basic VI relationships. So I'll recap those quickly. For a capacitor, we have the current is equal to the capacitance times the time rate of change of the capacitor voltage. We can also put that in integral form, and we can do the same for the inductor. We have that the inductor voltage is equal to the inductance times the time rate of change of inductor current. We also have that the inductor current is equal to the initial current plus 1 over L integral from T0 to T of the inductor voltage. Now, capacitance we've defined as the change in charge stored divided by the change in voltage across the capacitance. And for inductance, we've said that it is equal to the change in flux linkage, which is, remember, volt seconds, divided by the change in current. Okay, and we also are going to make use of diodes and transistors, okay, but in a very simplistic fashion. So we're going to have other devices. We're going to have, initially here, we're going to have just ideal diodes, where we have VF is going to be equal to 0 for any current that's greater than 0, and we'll have the current equal to 0 for any voltage less than 0. So it's either a short or it's an open. And then we'll have transistors as well. Okay, well, I'll call this ideal switch transistor. And so we'll think of, here we'll use a MOSFET, and we'll use an N-channel MOSFET. We have a drain, a gate, and a source. And here we'd have VGS across here, and we'd have IDS, and we have the voltage from drain to source, VDS. And we will say that it is an open for VGS less than V threshold, some VT threshold there. And it's going to be a short for, this is drain and this is source, for any VGS greater than threshold. Now we could augment this later and consider, adding a drain to source resistor. And just like we could consider with this, we could consider adding a voltage drop, such as 0.7 volts. Okay, but that's not going to change the principle of operation when we look at a switching converter that utilizes diodes and switches. So for this initial introduction, we're going to assume completely ideal switches and diodes. They're shorts or they're opens. Okay, and a couple more things I should mention on the capacitor and the inductor. Energy storage. So we have energy stored in a capacitor is going to be equal to 1/2 the capacitance times its voltage squared. And the energy stored in an inductor is going to be equal to 1/2 L times the current squared. So now let's start looking at the DC-DC converters, or switch mode power converters, of which the boost converter is a member. So I've drawn here a basic, just a block representation of a DC to DC converter. It's a power supply. It would take a voltage Vn that would be supplying some input current In, and it would convert that energy, that power, V times I, and then deliver a voltage, in most cases, to a load. Here I've represented as a load resistor RL, and when that voltage is applied across that load resistor, there's a current that flows IO. And so there's an input power, Vn times In, and there's an output power, VO times IO. And one of the really important characteristics or figures of merit for a converter, a DC to DC converter, is its power efficiency. In other words, how much output power do you get for a given amount of input power? Or otherwise put, how much of every watt that goes in actually comes out and is delivered to the load. Now, of course, it's going to be less than 100%. We can't generate free energy, but it can be very close to 100%. So depending on the particular design of the converter, the voltages and the currents that are at play, you could have efficiencies that range anywhere from, say, 70% all the way up to high 90s, perhaps as high as 98, 99%, and some more rare, but in some cases. And this is fundamentally different than another class of power supplies, which is called linear regulators, linear voltage regulators, a class of voltage or power converters that are simple to use, but they are inefficient. Their efficiency is typically related to just the ratio of voltages. So it might be, it would be something like the efficiency is the output voltage over the input voltage. That means that if you were supplying, say, 12 volts or to the converter and you were getting 3 volts out, okay? Whereas a switch mode power converter could do that theoretically at 100% efficiency. A conventional linear regulator, sometimes they're called series pass regulators, would have an efficiency that would be a theoretical efficiency that would be no more than 3 over 12, in other words 25%. Okay, so DC to DC converters really offer some critical high power efficiencies that other types of power converters cannot offer. And we're going to see another special feature of DC-DC converters in this lesson here, where we're going to talk about the boost converter. And that's the ability of a switch mode power converter, or a DC-DC converter, to be able to produce a voltage at the output that's actually higher than the voltage at the input. And that is in fact what a boost converter does. So we'll see this shortly, but V out is going to be greater than V in. There's another converter that we won't talk about here, but it's called the buck converter, and it is useful in when you're trying to convert a voltage down to a lower voltage. Here I've drawn the schematic of the buck converter, and you notice it looks very similar to the boost converter. In fact, it has all the same elements, they're just rearranged. The switch, S, has been swapped with the diode, and the inductor has then been swapped. I should say the inductor and diode have been swapped, and then after that the diode and the switch have been swapped. So we're going to just talk about the boost converter today. Okay, so here's the boost converter, what the circuit looks like, and you will in lab be building something very much like this. It really is nothing more, at least in principle, than an inductor, a switch, which here we're representing as a MOSFET transistor. That's a typical device that would be used because we switch this very quickly, and then a diode. Those are the three main elements. And then I guess fourthly we have to include a capacitor, which is storing charge for us. So an inductor, a capacitor, a switch, and a diode. And that comprises the basic power stage of a boost converter. So boost power stage. Now the reason I say power stage as opposed to just boost converter is that this does not comprise, or this diagram does not show a complete power supply. So we'll see that the way that you regulate the output voltage, Vout, is by changing the width of these pulses that are sent to this switch. The switch is turned on and off rapidly, but we vary not the frequency typically, although sometimes that's done, but here we'll talk about actually just varying the duty cycle, the percentage of time that the voltage at the gate is greater than a threshold, the threshold voltage meaning that whenever the percentage of time that the transistor is on compared to its period that it's switching at. And there is a feedback system. There's more electronic circuitry that surrounds this converter that will measure the output voltage, compare the output voltage to a voltage that you desire. We'll call it a reference voltage, much like the reference temperature, like in your home automation or home temperature thermostat to regulate heat, or the AC to keep you comfortable at home. Same thing here. You have a voltage reference. You feed the output voltage back to a circuit that compares it to the desired voltage, and then there's circuitry that then will make recommendations or changes to the pulse train going to the transistor. Mainly it will change the duty cycle, either increasing or decreasing based on whether you have too little or too much voltage in the output. Now what we'll be doing in the lab, we'll be just building this power supply, or this power stage. We will not be building an entire supply. And the pulses that we will be supplying to our transistor will come from a function generator and not from some control circuit that is monitoring the output voltage and then changing the duty cycle dynamically. So it's kind of like running the engine on your car without some cruise control, right? That's looking at the speed and adjusting the throttle. We're going to run it what we say open loop. Okay, I want to now talk about the basic operation of the boost converter, and it really hinges significantly on the characteristic of an inductor and then of a capacitor. So let's suppose that we had a battery, and we'll say it was 3 volts. Or I should say, no, I don't want a battery. Take that back. Let's say I have some voltage source, and we'll say that it's 3 volts, and I want to charge a battery over here that is 6 volts. And of course, if I were to just connect, let's say I put a resistor and I connect the voltage source to this battery, I'm not going to get any charging, right? In fact, what I'll get is the current going to my output here will be less than 0, right? And current will actually be flowing out, and I won't ever be able to charge my battery. And of course we say, haha, I can trick this current by putting in a diode. Okay, sure, you can put a diode in, and now we can say the current is no longer less than 0. But is the current ever greater than 0? No, it's never going to be greater than 0. In fact, we can just take this resistor out, and what we have is we will have the voltage across this diode will be 3 volts minus 6 volts, or minus 3 volts, and it will be off. And so we're not going to get any current to flow from our voltage source up to our battery to charge our battery. So here enters the inductor. So what we're going to do is we're going to put an inductor in here. Now at first, when we put an inductor in and we connect this up, if the initial current through the inductor is 0, nothing happens, right? We're still at 0 amps. But now let's suppose that this current, IL, at time 0 was actually equal to some initial current, I naught. Okay. Now if the current is actually positive, remember that an inductor, the current cannot change in 0 time. We have VL is equal to L di dt. In other words, VL over L is equal to di dt. So all we can say is that we can instantaneously change the rate at which current will increase or decrease in the inductor, but we can't just change it immediately. It's completely analogous to saying you can't change the velocity of a mass instantaneously unless you had infinite force. Similarly here, we'd have to have infinite voltage. So if there is an initial current in this inductor, then all we can do is we can affect the rate at which that current increases or decreases. So if this is greater than 0, okay, then we would have the following circuit. We would have the diode being on, and we're going to treat it as a short. And we'll have 6 volts, we'll have 3 volts, we have L, and we have our current IL. And the voltage across the inductor here is, in general, it's V in minus V out, if I call this V out here, and this V in. But it's going to be equal specifically in this case to minus 3 volts. So, and let's say that our inductor is equal to 1 Henry. So VL over L is going to be minus 3 volts over 1 Henry, which is minus 3 amps per second. So what does that look like? If we plotted the current versus time, it starts at I.O. and then it just goes down. And it goes down at a rate of Vn minus Vo over L, which in this case is minus 3 amps per second. And as long as the current is positive, the diode will be on. But once it reaches 0 and the current is no longer 0, if the diode were not there, then this thing would keep going. Okay? If diode not present. In other words, if it was a short. Right? So it would just keep going. But it doesn't, because the diode stops it. Okay? So the interesting thing here is that if the inductor had some initial current, then we could actually cause current to flow from the voltage source to our battery. In fact, let's consider how much current actually does, how much energy do we transfer? Well, if we look at this area under the curve here, right? And let's say that our current initially is equal to 6 amps. So since we're going at minus 3 amps per second, this is going to be 2 seconds, right? And so what is the area under this curve? What does it mean? Well, we have coulombs per second versus seconds, and so this area is charge, right? So we have 6 amps times 2 seconds, and we have to take 1/2 because it's a triangle, so we end up with 6 coulombs. All right. Now, we can say the input, the energy delivered by the input source is going to be equal to Vn times the amount of charge that was delivered. And the amount of charge that was delivered is going to be equal to our 6 coulombs. Right? That's coming from right here. So we just, and remember, voltage is joules per second. Joules per coulomb. So we just delivered 18 joules of energy. From that inductor took 18 joules of energy from the from our voltage source Vn. Now, what about what went to the output? That is to our output battery. Well, there it would be V out times delta Q. Now, all of the same charge was delivered to V out, right? So that's going to be equal to 6 volts times 6 coulombs, which is 36 joules, right? Now, wait a minute. It looks like we're able to deliver more energy to our output battery than we were required to provide from our input voltage. But of course, this can't be true, right? We also started with some energy in the inductor. The energy in the inductor is 1/2 L I squared, right? And so that was 1/2 times 1 Henry times the initial current we said was 6 amps, so that's 6 amps squared. So that gives us 36 over 2, or 18 joules. Well, looky there. So what we have is we have Vn supplies 18 joules to the output, and the inductor supplies 18 joules to the output. And the vehicle for allowing our diode to conduct and to basically provide a mechanism for charge to flow uphill, if you will, from a lower potential to a higher potential is the inertia, if you will, of the inductor. Okay? And so this circuit that I've just drawn with the voltage source, the L, the D diode, and the output battery is the boost converter minus the switch. So I can go back in here and draw the switch, but I'm going to say S is off. Okay? In fact, we haven't seen yet what usefulness it actually has, but here's where it will become useful. We just willed that the inductor had an initial current of 6 amps, right? We didn't talk about how do you get 6 amps? How do you get current to flow in that inductor at first? We acknowledge that if you just simply put an inductor in series with this diode, which the two together connected the 3 volts to the 6 volts, no current's going to start flowing in the inductor. We first had to assume that there was current in the inductor. And the way that we get current to flow in the inductor is by doing this clever little thing. Now, let's consider what happens if our switch is closed. Okay, now we'll have our 3-volt source and our inductor, and then when we turn on our switch, we basically short to ground. We have our diode here, and we have our output voltage. That's 6 volts. Now the voltage across the diode at this point is going to be what? It'll be minus V out, or minus 6 volts. So this is off. In other words, there's no way you can turn on the switch and also have the diode on. Because as soon as you turn on the switch, you're grounding the anode side, that is this side here of the diode, and the cathode side of the diode, the right, is tied up to 6 volts. So immediately you're going to reverse bias the diode will be off. That means there is no current flowing to the output. So I out is equal to 0 during this time. That seems ineffective initially, right? We're trying to get current to the output. But we've already seen that if you do have current flowing in the inductor, you can get current to flow uphill and deliver energy to the output, or current and charge to the output. So that's good. Right now what we need to do is just to look for a mechanism by which we can put some energy into the inductor before we connect the inductor through the diode up to the output and leverage off of the ability of the inductor to push charge uphill, potentially. So what do we have from the vantage point of the inductor here? What does it see? It has a voltage VL that is equal to simply the input voltage. Okay, so if I were to plot the inductor current versus time, and we start at 0 with no current, if I turn on the switch, so let's do this, I turn on so this is the switch state. Okay, what that means is this would actually be like VGS, okay? And I'll plot here the voltage V, call this, we'll ground this, and I'll say this is VS, okay, for the voltage across the switch. It's really the drain to source voltage, so VS. When I turn on the switch, the voltage across the switch goes to 0, okay? And when the voltage across is 0 across the switch, the voltage across the inductor is Vn. And so the current rises. And it rises at a rate of Vn over L. And how long does it rise for? It's going to rise for a duration of however wide our pulse width is. So I mentioned that our converter puts out a duty cycle or a pulsing signal. It will actually have I'll draw it larger here. We've got a period T, and we have an on time of duty cycle times T, right? Where duty cycle is going to range from 0 to 100%. So this period will be D times our period. And so the current at the end, at this point here, will be equal to Vn times, or Vn over L times the period times the duty cycle. If I leave the switch on twice as long, the current will climb to twice as high a value. Notice that during this time, the current from the input source, the 3-volt source, is the inductor current. So the current from the source is rising, but yet the current going to the output is 0. Okay? Now, when we turn off the switch, the inductor current does not change instantaneously. Okay? But what will happen is when we turn off the switch, we'll go back to this circuit right here, right? Or drawn otherwise right here. The switch is off. And now the current is flowing from the input 3 volts to the output 6 volts. And we have a voltage across the inductor that is going to be equal to Vin minus V out. And the slope that we experience, the inductor current experiences, is Vn minus V out over L. And in this case, it'll be 3 minus 6 over 1 Henry. So that will be equal to minus 3 amps per second. And this was equal to plus 3 amps per second. And so the current will fall back down. Now if I were to plot the, let's see, the diode current during this time, let me see if I can, actually first what I should do is Vs. Vs, notice that when you turn off the switch, the voltage Vs right here rises from 0 when the switch was on up to the output voltage V out. Okay, so this goes up to V out. And then eventually this will do the same thing here. Turn it back on. Okay, now if I was plotting the input current, okay, the input current is this here is this is equal to the input current as well. If I was plotting the switch current, what is the switch current going to look like? It'll look like this, and then it'll actually go to 0, because when I turn the switch off, no current flows through the switch. Okay, this is the switch current. Draw it over here, I switch. And the diode current is going to look like this. This will be ID, where we would draw, okay, it's kind of crowded here. This is ID, and this is also equal to I out. Okay, it's actually the current that is going through the 6-volt source. So notice that when you add these two together, you end up getting the input current IL. Okay? So, what have we learned so far? Time to go to another page here. Oops, freezing up. Okay. So again, the recap on how this works is that we can't get charge to flow uphill, potentially, without using an inductor, an element that has inertia, if you will. We recognize that if there's initial current flowing through the inductor, that will carry charge from Vn to the output, thereby delivering energy not only from the input source to the output, but also from the inductor to the output. Once the inductor current has expended all of its energy, then the question is, how do we replenish energy in the inductor? And the way that we do that is by turning on the switch which applies all of Vn across the inductor, and then during that period of time, when the switch is on, the input voltage supplies energy only to the inductor, not to the output. It charges up the inductor, enabling the charge transport uphill the next time that we turn the switch off. Now let's let's try to come up with an input-output voltage relationship. Draw this waveform again. So we have, if I plot IL, we have voltage rising at Vn over L rate, and then I'm going to have current falling at Vn minus V out over L. Now, there are different ways that the converter can be run. One of the ways is that you can let the current sit there at 0 for a while, and then you turn, after a time, you turn the switch on again, turn it off. So here we would say S on, here we would say diode on, and here we'd say everybody's off. Okay, then we'd have S on, here's diode on, and of course when S is on, diode is off. When diode is on, S is off, and so forth. And here everybody's off. This is called discontinuous conduction mode. This is one of the modes that the circuit can work in. Now, we're not going to focus on this one at this point. In this lesson, I want to take you through the case as I described just above, where the current rises at a rate, it falls in general at a different rate, though knowing the way I've drawn it is I picked this special case where the output voltage was twice the input voltage, and so you get this nice symmetry. But in general, it's Vn over L, and it's Vn minus Vo over L, and so this waveform may look skewed in some cases. In other words, it may look like something like this, like that. That's totally appropriate. Okay, or it could look the other way, where a lower slope initially and a sharper slope on the fall. But if we turn the inductor back on right when it reaches a minimum there, and we continue to do this, okay, then what we have is that we incur over this period of time some change in current. Right? That change of current is going to be Vn over L. That's the rate. And remember, the length of time that we apply this is for our duty cycle times our period. Okay? So this is delta I right here. And on the falling side, I can't draw it as well here, I'm cramped, but if it's, do this, so we'll call it delta I, I'll say negative, okay, because it's falling, positive here. This would be Vn minus Vo over L. And now it's not on for a duty cycle like D times Ts, it's on for the remainder of the period, which can be written as period times 1 minus D. So if D is 20%, if the switch is on 20%, it's off for 80%. All right? And if we're going to have this condition where, let's say this is equal to time 0, this is time t, this is time 2t. So if we say IL of, let's say t is equal to IL of 0, which is equal to IL of 2t, which is equal in general to IL of n times t. In other words, the circuit is in equilibrium, what we call equilibrium, or it's in steady state. So, of course, if we started with current at 0, this thing gets going. Eventually, it'll arrive at some current, average current, and it's not going to change from cycle to cycle. So, if we assume that our converter is going to be operating in a equilibrium state where the current from cycle to cycle is not changing. Now, of course, it goes up and down every cycle, but if it comes back to the same spot that it started from the previous cycle, then we say it's in equilibrium. And so we want to find what that relation or that condition is. We would say this happens when, say, steady state, when delta IP plus delta IN is equal to 0. Okay, so that means Vn over L times D times T is equal to Vn minus VO over L times 1 minus D times T. Now notice, this is very critical here, that that the inductance and the period can be eliminated. Okay, in other words, we're going to find a relationship between the input and the output voltage in the duty cycle that doesn't depend on the value of the inductor and doesn't depend on the frequency. So let's rewrite this. We have Vn times D is equal to Vn minus VO times 1 minus D. Let's collect Vn over here. We have D. Let's see, what do we have here? Vn minus 1 here, and over on the other side we have, wait a minute, I have an error here. This is quantity. Okay, let's start this over again. Vn times D, and then we're going to bring minus 1 plus D. Oh, I'm sorry. See, I made these equal. Those are not equal. They're added, right? We add them here. We add them. Okay, let's do this again. Vn times D, and now we have plus 1 minus D plus, well, then we'll do the VO on the other side, equal to VO times 1 minus D. These cross out, and we end up with VO is equal to Vn times 1 over 1 minus D. Sometimes 1 minus D is defined as D prime, just as a, if that shows up somewhere, so you know what it means. So this is very interesting. If we plot the voltage V out versus duty cycle, okay, and maybe we can even plot V out over Vn, what we'll find is that at a duty cycle of 0, this starts at 1. Okay, and this goes up to duty cycle of 100%. At a duty cycle of 0.5 or 50%, we would have Vn over 1 minus 50%, in other words, 2 Vn. So we have a data point here, we have another data point here. If we went to 3/4, 75% duty cycle, then we have Vn over 1 minus 3/4, in other words, 4 Vn. So now we have this value. And you can see this is going to take off and go very rapidly through the roof. And in fact, this is so crazy that the limit as D goes to 1 is that VO would go to infinity, theoretically. Of course, that's not going to happen in real life. And one of the main reasons is that when you look at this circuit, this original boost circuit here, notice there's nothing lossy in it. I have no resistors. And so there's no place for energy to ever be dissipated in this circuit other than the load itself, which is represented as a resistor. And dissipating power in the load is fine. That we've achieved our goal. We've delivered power to our load. So the reality, though, is there's resistance in the MOSFET channel. There's voltage drop and resistance in a diode. There's resistance in an inductor because it's wound with copper, typically copper wire. There's resistance in a capacitor just in its construction, and so any kind of currents that's flowing back and forth in that capacitor will end up causing I squared R losses. And there's other types of losses that we won't talk about here, but they fall under either magnetic core losses, like losses due to the magnetic material in the inductor, or they're switching losses due to turning the transistor and the diodes on and off at high rates, and the fact that they don't actually switch in zero time. So all that to say that an actual converter in the lab is not going to run at 100% efficiency, but they can approach 100%. And so let me go back here. And just to recap then, what we have is that if we apply a driving signal, PWM signal, to a MOSFET, so this would be VGS, we would find that a voltage across our VDS on our switch would look something like this, where it would go approximately up to V out, and it would go down to approximately 0 volts. We would have an inductor current that will actually rise and then fall and rise and fall. Okay, and I did not mention this previously up to now, but we had assumed that the initial current here was 0. Okay, recall when I did this analysis here, we started this out at 0 right here. Then when we looked at the case where we're in equilibrium, where when the current starts out at some initial condition and it goes up and then comes back down to that same point, we did not actually assume at that point that IL of 0, or IL of T0 if you will, was 0. In fact, it can be any current. So it turns out that the relationship here for the output voltage as a function of the input voltage, at least theoretically, does not depend on the actual average current that is flowing through the inductor. This average current here, this is IL, capital IL. This, remember, is the current flowing in from our converter. So it's this here, IN is IL. They're in series. So this average input current, or average inductor current, is the average input current. Furthermore, we can plot the diode, or the switch current, as looking like this here. It'll jump up here. So this is going to be I of the switch. And then lastly, we'll have, let's see, we'll do the inductor current, not the inductor current, the diode current, and it will look like this. So this will be I diode. And notice again that these two, if you add them together, give you the inductor current. And of course that has to be, because if you look back at the circuit here, if you do KCL right at this point, the inductor current is supplying current into that node, and that inductor current goes either through the diode or through the switch. And we've already made the case that the diode and the switch can't be on at the same time. So at any one time, the current through the diode or the current through the switch is 0, leaving the other conducting member to carry all of the input current. Okay. So the last thing I want to talk about then, I guess, in closing, is to kind of go back to the beginning and not avoid the question, which is, how did you go from, we jumped over to using a battery, saying this idea that we're going to charge a battery, but yet when I first drew the boost converter, I did not show a battery. I showed a capacitor and a resistor. And I don't want to take the time now to go into much detail on it, other than to say that if you look at the amount of, I guess I should do this one other thing, that the current, this will maybe help, the current flowing through, the average current of the diode will be here, right? We could calculate this pretty easily. It's going to involve the duty cycle, it's going to involve the peak value of the inductor and the minimum value of the inductor current. In fact, I can actually write it out. It's going to be equal to the input current, which is the average inductor current. Inductor current times 1 minus the duty cycle. And the average transistor current, just a second here, undo, is going to be, this is going to be the average switch current. It will be the inductor current times the duty cycle. Okay, so back to this question about the capacitor and the resistor. The average current flowing to the output, I.O., okay, this I.O. here, but if you look at the average value, is going to be equal to I.L. times 1 minus the duty cycle. So if I were to take this, let me just see if I can bring this down here and wrap this up. Come on. My journal program crashes sometimes or gets really sluggish and I have to restart it. Okay, so come on. So the average current flowing out here is going to be, or I should say the average current through here, ID is equal to IL times 1 minus D. That comes straight from the fact that you have IL, on average you have IL flowing through the inductor, and for D percentage of the time you have that current flowing down through the switch, and for the other 1 minus D percent of the time you have that current flowing through the diode. And the average current through this inductor or this capacitor, if the circuit is in equilibrium, meaning that the voltage isn't growing cycle by cycle, must be equal to 0, which means that on average the voltage or the current to the load is also equal to ID, which is equal to IL times 1 minus D. Okay. Now if we if we look at this a little more closely, we could find that the current going through the capacitor, okay, is actually, let me move this over for a second here. The current through the capacitor, if I were to draw IC here, what it's going to look like is it's going to be this waveform here, okay, with the average, this is 0, this is IC. It's simply, IC is equal to I of the diode minus I flowing out of the, I out, which is, this is just equal to IL times 1 minus D, okay, which is actually what that is. And so what will happen is the voltage on the capacitor will kind of go up and down. I'm not going to try to figure out what that is, but that voltage is just simply the integral, VC is equal to 1 over C, the integral of the excuse me, capacitor current. If you make this large, very large, then this delta VC, if we call this voltage here, will be much, much less than the average voltage across the capacitor. And this will lead us to approximating this as just a voltage source. Excuse me, I'm sorry. So that's how how we justify leaving the capacitor out. If we actually had considered the capacitor and the resistor in the analysis, it would be tremendously more complicated. Now, if you're trying to answer some specific questions about the details of that ripple voltage, other things, you have to go into not making the assumptions we have, the simplifying assumptions of using the voltage source V out. But if what you're really looking for is just to establish the input-output voltage relationship, like this one here, and getting a basic understanding of the waveforms like we did here, then making the assumption that the output capacitor and resistor is just a voltage source is fine. The tricky part is that that voltage source V out, okay, and I'll close with this, that this voltage source V out, normally we think of that as an independent source, so maybe I should actually draw it as a triangle. Its value in the end is going to be equal to RL times IO, which is actually RL times, if you remember, IL times the 1 minus the duty cycle. Okay, so it's not like we literally have a voltage source there. It's that we have a capacitor and a resistor that over a switching period doesn't change its voltage much, and so therefore we think of it, or we can treat it as having a fairly constant voltage. But in the long run, if it's going to stay a constant voltage, we have to satisfy the condition that the average current flowing into that cap is going to be 0. Otherwise, the voltage across that cap would be integrating up or down. So I think I'll stop here. Wait, let me say one last thing on what the circuit is that will be built in lab. So you will take a 3-volt source. There'll be a bench power supply. You'll use an inductor that you'll actually wind. It's going to be a toroid, and you'll put windings around it. So you'll have two wires. You'll use a 2N7000 MOSFET like you have used before. You'll connect this to a function generator to generate a pulse, likely 500 kilohertz, 0 to 5 volts, and you'll vary the duty cycle. Okay, and then you'll use a 1N4148, basically a little signal diode. And the goal here is that we want to light up some LEDs, some white LEDs, 3 of them. Now nominally they're about 2.8 volts each, so that means you're going to need at least somewhere between 8 and 9 volts to turn this on. I have a little capacitor here to provide some filtering. Okay, and lastly, we'll put in a little resistance to ground, because that will allow us then to measure the current, and we'll also even be able to, if we take this capacitor out, this voltage here will be equal to, call this RS times ID. So remember that current that looks like this? You'd actually be able to see that here if you take that capacitor off temporarily. So that you'll hear more about that. But that's the basic lab that you're going to run. You will light up 3 white LEDs in series using a 3-volt source by building the simple boost converter.